Okay, so today I'm going to talk about angular momentum. So first, what is angular momentum? So angular momentum, a measure of the momentum of a body in rotational motion. In a spinning sphere will continue to spin unless acted on by an outside force. And a change in angular momentum are equivalent to torque. But actually, you can see it here. Sorry. L, which is the angular momentum, okay, is the cross product of R and P. So take this picture for example. This is the origin, and here is the P, which is the momentum, so which is also equal to mv. Okay, and okay, but now we're calculating the cross product, so we don't just times R and P, because that leaves me there's an angle called theta here. And remember, it has to be vertical to R. The P has to be vertical to R. So this distance, I use green, okay. So this distance equal to this distance. So this is equal to P sine theta. Okay. So here and this is vertical. So the L equals to RP sine theta, like that. Okay. And now you can see, so L equal to RP sine theta, and remember P equal to mv, and remember this and V, the V is mv, okay. And okay, so now you can see, so now remember R equal to R mv sine theta, and now we delta, so delta L equal to R m delta V sine theta, so R m and delta V is equal to A times delta T. So R m A delta T sine theta, which is also equal to, because M A equal to F equal to MA, so which L is also, delta L is also equal to R F delta T sine theta. And while the R F sine theta equal to the torque tau, which is equal to tau delta T. Okay. Next. So I called rotational inertia. And rotational inertia. Yes, rotational inertia. Yes, okay. So rotational inertia. I think I skipped. Yes, okay. So rotational inertia is a property of an object which can be rotated. It's scalar value, which tells us how difficult to change the rotational velocity of an object around a given rotational axis. And rotational inertia plays a similar in the rotational mechanics. So to mass in linear mechanics, and the rotational inertia of an object depends on its mass. And it also depends on the distribution of the mass relative to the axis of rotation. Rotational inertia is have a symbol of I. Okay. So the I just said rotational inertia equal to mr squared. So why? So first, Ft equals to MAG. So remember, AT is not equal to AC. So what is AT? Like a ball is in circular motion. So this acceleration is AT. What is the center? This is AC. So that we're looking at the AT. So Ft equal to MAT, of course. F equal to MA, Ft equal to MR alpha, of course. And the Ft, and we type both side by R. So we get FTR equal to MR alpha R, and FTR equals to tau. So tau equal to MR squared alpha. And we just group this equal something, and we get equal to I alpha. So I equal to this, so I equal to MR squared. So for exercise 1 part A. A motor capable of producing a constant torque of 100 Newton meter and a maximum rotational speed of 150 radians per second, and connects your valve with rotational inertia 0.1 kilograms meter square. What's the angular acceleration for the valve experienced as a motor switch on? So now you can see. Now you can see what we get. So now you can see we got a torque. Okay, so we got a torque. We get speed. We get rotational inertia, maximum rotational speed, and we get angular acceleration. Well, no, we don't. We are going to find the angular acceleration. So how to solve this question? Simple. Remember, we get torque, rotational inertia, acting like alpha. So remember, we just see a formula right here, right? Tau equal to I alpha. Tau how much? 100 equals to 0.1 times alpha. So alpha equal to 1000. Okay, so let's check the answer. Yes, 1000. And exercise 1b. So according to the last question, how long will firework take to reach a steady speed if starting from the rest? So now we already know alpha equal to 1000 rad per second squared. And remember, there's still one thing we didn't use, which is the maximum rotational speed, which is 150. And max v equals okay, so v max equals to 150. And remember what? V equal to V0 plus AT. Remember, you know this, right? So this is this. 150 equal to V0. So V0 is set at where? Okay, here it says start from rest, which means it's 0 plus this acceleration now is alpha, which is 1 t, right? So you can calculate. So it goes t equals to 0.15. So let's check the answer. 0.15 seconds. Okay. And how can we calculate the rotational inertia in general? So first, rotational inertia equals to total rotational inertia. What does that mean? That means if here, under straight, clear. Okay. So like here is the axis. Right here first, we get a ball of M1, and with this, we don't like this color. Okay, with here, I don't like this color. With R1, and another ball here, M2, R2. Okay, and remember, I equal to NR squared, right? So rotational inertia for M1, I would say I1 equal to M1 R1 squared, while I2 equal to M2 R2 squared. So if we want to calculate the I, we will calculate the total. I will calculate the total I equals to all the rotational inertia, the sum of the rotational inertia. So let's see. So it will just be I1 plus I2. So if there's 3 or more, it's just I1 plus I2 plus I3 like that, and so on. So which is equal to M1 R1 squared, M2 R2 squared, and so on. Okay. So like that. So exercise 2, part 8. Consider an object shown in a figure below. What is its rotational inertia? So rotational inertia, remember, which is we just calculate all of them together. And remember, it is the sigma of I, right? So sigma of I, how much? So first, remember I equal to mr squared. So if we have the same r, we can just use r squared and here, which is maybe m1 plus m2, if they all have the same r, right? Yes, okay. So if this is so, then we can look at this question. So now we can see this 1 kilogram, this one. So we will find that both of and this 1 kilogram and 2 kilogram have the radius of 0.75 meters, right? Yes. So which means that the I equals to, which is 1 plus 2 times 0.75 square plus here we have, which is 1 times 1 square plus 1 times 1.5 square, which is equal to 3 times 0.75 square plus 3.25. Okay, so how much is it? So we can use a calculator, will be good. So first, okay, so 3 times 0.75 plus 3.25 plus 4.25 and wait, but you can see something. Let me see. Oh, so it's 3 times this. No, here's a square. So which is 4.9375. 4.9375. And the answer is 4.9375. Exercise 2B. So consider the alternate case of the figure below. System 1 will be the rotation of this. And this, I don't know, okay? Because it's being blocked by the picture, okay? So, but it's just asking you to calculate the rotational inertia. So this is very, very, very simple. Why? Because all the r are equal to 0.5 meters, which means sigma I equal to r squared sigma m, which is equals to r, which is equal to 0.25, and sigma m 1 plus 1 plus 2 plus 1, which is equal to 5. Equal to 1.25. Okay? Okay, the final rotation inertia of complex shape. So why? Because now we are looking at for one path. So now if you're looking at a rod like that, if you are looking at a rod, you have to plus this, all of them together. So if you can get this formula, so for a cylinder, just plus them together, you can get this. So it's just formula. Okay. So exercise 3. If our shape is down in figure 5, right here, when freeze to each of them with a mass 50 to a steel ring which mass 10 is about the center of the object. Okay, so first, rotation inertia. So first, we will calculate it. So let's see. So first, if you just think you just add the mass together, you will find right here a cylinder is mr squared 2. It will be very happy, right? Yes. Okay. Which means that, and they have the same distance, which is from here to here, or is it here to here, here to here, They're all the same distance, right? Yes. So you can just actually just calculate. But first, how much is this distance? Right? So this distance equals to 1 plus 0.75 divided by 2, which is equal to 1.75 divided by 2. 0.875. 0.875. So we got 0.8. Okay. So first. So sigma I equals to, maybe you will think 0.875 squared times how much? 50 times 3 plus 100. This is 150. This is 100. This is times 250. But you forgot one thing. That actually in this question, this plate have rotational inertia too. Itself. Okay? So how do you calculate this? And then you go back. See here. A cylinder which is half mr squared. So for this plate, it's a cylinder, right? Because it's it have a free and this, right? So you also have to plus what? What's the rotational inertia? Equals to m, how much? 50. Wait, half 50 times r squared, and I'll just say 0.74 and 4, and this whole thing times 3, which is equals to times 250 and plus 25 times 0.64, right? And times 3, right? Yes. Okay. 4 times 3. So wait. That's times 250 plus 50 kilograms half and r squared times 3. So 75. So let me rewrite. So let me explain again. Okay. So 1.75, which is the radius of these three things, and the total is 250 kilograms, and then plus this 3 of them with 50 kilograms, and 1/2 because according to here formula is 1/2. And r squared, which is 0.8 squared times 3. So actually this is just for it's got okay. Yes, this is a square times 250 plus 75 times 0.647. Okay, so it's equal to 239.40. So it's around 240. So it's around 240. Okay. And the end. Yeah, also the end. Okay. So now this is the end, remember? And also I have to tell you another thing. What? Yes. I will also tell you one thing. What? That tau right here equals to I omega y. So this is very, very, very simple because wait, not go to I alpha. Wait, no, la L. Okay, sorry, I'm wrong. That's how. L equals to I omega. So what? So this is I omega because it's n r squared omega. And remember what this equals to? L equals to L equals to RP, right? So first, n this times omega. So first, R omega to B, so it's MVR. And MV equals to P. Actually, L equals to RMV. So which is equal to I omega, because this is equal to MR N equals to MR squared times omega. So this is equal to MVR. Okay? And I'm done. And first, let me see.